Moving on now to vision transformers. So as already mentioned in the objective slide, understanding images requires global context, meaning that humans would generally need to appraise an entire visual scene to be able to describe what's going on. And convolutions, they never really give us this, as they're always learning very localized filters that require many layers of convolution and pooling to even detect parts of objects. And this is a particular problem for medical imaging tasks, since disease is often spread out across an entire organ, with the global pattern of disease very important for differentiating between different subtypes. For example, differentiating frontal temporal dementia from Alzheimer's, or to understand how human cognition is encoded by distributed biological neural networks, or to detect human metastases, or for image reconstruction and super resolution tasks. Vision transformers essentially work by patching up an image into sections, flattening those sections, and then treating it like any other sequence learning problem. We can see that these patches correspond to evenly sized regions of the original image. These patches are first flattened and then pass through a linear embedding layer to compress the sequence length to D. We then add positional encodings that I'll talk about in a couple of slides' time, and an extra token is added for learning the class for discriminative tasks. And we've seen this before in the Burt-Viz notebook, where it was called the CLS, or class token. These tokens are then passed to a transformer encoder, which applies multiple layers of multi-head self-attention and feed-forward layers. And then finally, for these discriminative tasks, classification or regression, MLP classification prediction head is added. So essentially, transformers are throwing away most of the inductive, or all of the inductive biases that make CNN such efficient learners, moving back up in scale from learning small 3x3 depth weights tensors to the much larger D/D weights tensors that are needed to encode queries, keys, and values for each attention head. So this results in about 4 times as many parameters as when compared to a broadly equivalent CNN, which puts us back at risk of overfitting. So one way of reinserting some degree of inductive bias back into the transformer framework is to add positional encodings, because this will at least give it some hard-coded understanding of how different elements of the sequence relate to one another. So one way to do this is to add sine-cosine functions where the specific combination of frequencies is unique to each position. And in this way, neighbouring positions on the y-axis here have similar Fourier transforms, with the distances being continuously encoded. For vision, of course, this needs to be extended from 1 dimensions to 2D or 3D. Many papers still use sine cosine embeddings to encode this, but in the original VIT or vision transformer paper, they actually learnt these embeddings, exactly how I'll explain in a minute. But the tiled figure on the right shows the cosine similarity between the positional embedding of the patch with the indicated rows and columns and the positional embeddings of all other patches, showing that these encodings are most similar for neighbouring patches or patches from the same row or column. For example, here we have column 2, row 6, and you can see that it's most similar with itself, its neighbouring patches, and the other patches in the same row and column. So just to clarify what a positional encoding vector looks like, they need to have length D. They need to have the same length as the input token embeddings, since what we want to do once we have them is add those 2 vectors together. Addition is used rather than concatenation to save memory and parameters. It is sufficient because these can be separated by the many layers of the network, with residual connections added to help ensure that this positional information isn't lost as it moves through the network. And then looking at their expressions, sine cosine embeddings are a d-dimensional vector built up from d over 2 spatial frequencies, where we only need half as many as we have dimensions, since we encode even dimensions with sine functions and odd dimensions with cosines. On the other hand, if we're learning the embedding, then we are instead representing them by a d-length weights tensor, which we learned during training. We need 1 for each token, so we have an n by d weights tensor that we need to learn. Now, putting this all together, we first take the input patches and we flatten them to vectors of length dn. So that's how many pixels we've got in each patch. And then we add one learnable token for the CLS or class token, giving us n+1 patches or tokens. These tokens are pushed through a linear projection layer, which reduces the token length to d, and then positional embeddings of equal length are added to each one of them. Okay, so x1, 0, so this is the token length after it's been projected onto a d-dimensional sequence. So x1, 0 plus e, the positional embedding at location 1 added. The resulting tokens are then pushed through into the transformer encoder composed of a series of MHSA and MLP layers. Next, we need to deal with the resulting explosion in learnt parameters. So one way to ensure that models don't overfit is to pre-train them with self-supervision. For example, through contrastive learning or masked pre-training. Some early contrastive learning approaches included MoCo, which takes pairs of tokens and forces the queries and keys of similar patches to be similar, where, to ensure that this relationship is known without having to make any assumptions, these pairs are actually the exact same patch, but just transformed slightly with augmentation. So this is one of the earliest methods for self-supervised pre-training of vision transformers. It was found that it helped learn global representations, but later papers suggested that this type of self-supervision would collapse to homogeneous representations across different layers and heads. For these reasons, the master autoencoder was then suggested in 2022. So the idea here is very simple. We're going to push to the network an input with most of its patches missing, and then we're going to train a model that's going to try and reconstruct the full image from this sparse input, where due to image redundancy, which means the tendency of adjacent regions in images to display very similar colours and textures, this missing fraction has to be very high, typically around 75% of the patches. And then for the masked autoencoder, or MAE, this encoder only sees the 25% of unmasked patches, which massively reduces the sequence length, which therefore reduces the computational complexity involved of encoding this data, which means that you can learn a much deeper network, which in turn can learn a much more nuanced hierarchy of self-attention representations, meaning that you're going to have a much more detailed understanding of the images that you're encoding. And the learning of this detailed encoder is supported during training with a decoding network, which takes the encoded 25% of the patches, projects them back to their original location in the sequence, adds empty tokens for the missing patches, pushes them through a lighter decoder whose job is just to reconstruct the full image using conventional image reconstruction losses like an MSE. And then after this pre-training process, the decoder is removed, and we just use the encoder for downstream tasks, leveraging the fact that the training of transformers is fully invariant to sequence length, with the weights only dependent on the token length D, meaning that for downstream tasks we can then just start to work again with the full unmasked sequence of length N. And then for video, it's a similar idea, but there's even more redundancy between patches because they will be similar in space and time, meaning that for video recognition tasks, we tend to mask up to 90% of the patches. So this can be done randomly, meaning that completely different patches are masked for each point in time, or you can apply tube-like masking such that we move one patch consistently over a period of time. This issue of computational complexity being linked to sequence length also puts a limit on the resolution of the patches that we can use, since the smaller the patches, the more tokens we will need, the more attention operations we will need to calculate, and that will require more GPU memory. Thus, people have since addressed this problem through designing hierarchical learning schemes such as the Swin transformer, which initially restricts attention to small windows of space with very high resolution patches. These windows are gradually pooled over time throughout the network, such that their receptive fields get larger, but the resolution of their patches gets lower. And at the bottleneck of the network, or at the lower, after all of the pooling stages, you end up back in the domain where you have coarse patches, tension across the whole image. Where obviously this pooling of windows is taking inspiration from CNNs. To try and improve the range of attention at the highest resolution, the SWIN actually calculates attention twice, once within a given window and then once within a shifted version of that window. So this one has been moved down to the middle. And that allows it to essentially infer attention between this section all the way down to here. It works by first learning self-attention within the original set of windows, where here the x to the L EMB and the x hat L actually represent recurrent connections that are adding the inputs to the outputs of these self-attention and MLP layers. The allocation of windows is then shifted, which means that essentially you're just reassigning patches, right? So some of the patches that were in this window have now been moved to another window, and the actual list of patches that correspond to each window is different, and that's it basically. But then you learn another multi-head self-attention layer and another feed-forward network where all the weights tensors for these operations are different to these ones. Once we do this, we can perform dense prediction tasks such as segmentation, where by this I mean that we need to assign a label for every location in space, and for that we need to be able to learn labels at high resolution, which means that we need high resolution patches, which means that we need a spin transformer. So we can do this by basically setting up a SWIN UNet. So we take the flavor of a UNet, convolutional UNet, and we instead build it with transformers or spin transformers. So exactly like a UNet, we have skip connections between layers of equivalent resolutions, with downsampling occurring between the SWIN transformer encoding blocks through patch merging, and then these patches are split up again through the decoding blocks here. Doing this, it was found in this paper anyway, that these spin transformers slightly outperformed fully convolutional or convolutional transformer hybrid architectures, with some indication that the attention mechanisms, which by the time you reach the bottleneck covering the entire whole image, are helping to prevent over-segmentation. But to my mind, one of the biggest advantages favouring uptake of transformer architectures for image understanding tasks is that, again, they're inherently interpretable, meaning that if you look at the attention scores between different tokens and compose these back into an image, you will see that the model attends to the semantic content of the image. For example, in this case, we're looking at the attention of the classification token or the CLS token with all of the image tokens or the image patches, meaning that this is what the model needed to attend to in order to make an accurate classification that the foreground object is a plane. And indeed, by the time you reach these deeper layers, you see that most of the attention of the CLS token is focused on that aeroplane. We can't look at attention between all tokens, because then we'd be generating these images for every single token pair for every single layer. It's not feasible. So for discriminative tasks, we tend to look at the CLS token, and to simplify things further, we can aggregate attention maps across layers through averaging or multiplying the attention maps obtained from each layer. One model that excels in focusing its attention is Dino from Meta, where these benefits can arguably be traced to its unique training strategy. So like MoCo, Dino is trained through contrastive self-supervised learning. In other words, it is training the network to encourage similar patches to learn similar semantic meanings. However, unlike MoCo, Dino achieves this through what different training strategy known as self-distillation, where a student transformer is trained to match the output probability distribution of a teacher transformer using a cross-entropy loss. This system is using a multi-crop strategy, passing small local patches to the student and large global views to the teacher to force the model to learn local to global spatial correspondence. This strategy then means that it learns to encode the semantic context or meaning of different patches and how they relate to each other exceptionally well, generating extremely high resolution and detailed attention maps that are good enough to segment the semantic content from their images. Finally, it probably is worth quickly mentioning that it isn't only the attention mechanism that helps transformers learn. Experiments with incorporating some of their other engineering advances into convolutional neural networks has shown that these too significantly boost performance. For example, in 2022, the Convex paper tried inserting a range of VIT training tricks, including performing aggressive downsampling with 4x4 convolutions with a stride of 4 to simulate patching. They applied group convolutions, which are similar to the weighted sum operation applied in self-attention to calculate the queries and keys. They tried changing ReLUs to GeLUs. They tried a whole bunch of different tricks and found that when you put all of these additional features in, including much larger kernel slices, they could train CNNs that they said outperformed SWIN transformers on ImageNet classification tasks. So read from that what you will. Okay, in summary, for vision transformers, VITs are treating images like language by patching up the scene into smaller regions that get tokenized and then pass through the exact same transformer architecture as would be used for language. They learn more parameters, which puts them at risk of overfitting, but we can address this through hard coding positions with sine cosine embeddings and performing self-supervised pre-training. This is also true of language models. The other issue is complexity, which scales with sequence length. As this impacts memory requirements, there is always a limit. People tend to deal with this through hierarchical shifted window attention mechanisms. And the big advantage of all these frameworks, I think, is that transformers are inherently interpretable.